So now let's discuss about the scaling laws in turbine. So this is just similar to what we have discussed for the pump. For the pump you had head, the discharge was important, how much discharge it can deliver or how much the head rise. Okay, but here what is important is for a given head available how much power it can deliver. That is what is important for the turbine. So here when you do the scaling, the power delivered is a function of h, speed, and other factors. Okay, the diameter of the Pelton wheel or the diameter of the Francis turbine. When you do all this, so when you do all this non-dimensional analysis, okay, so this when you do all this non-dimensional analysis, it leads to non-dimensional numbers, something like this: ch, cq, and other factors, Reynolds number. But most important is the cp and cq. So how is this cp comes out? This comes out from the dimensional analysis in this form: power coefficient. The head coefficient is gh by n square d square, and the discharge coefficient is q and dq. So there might be densities and all that way. So these are your non-dimensional numbers. Okay, and they don't change. They don't change with operating response. Okay. Okay, so what I mean to say is that your p by n cube t power 5 for the model and p by n cube t power 5 for prototype is same. Your ch is same, that is h n square d square for model is same as h n square d square for the prototype. So two things: scaling and change in operating response. That is keeping the same geometry, but your if head is changing, what is happening to the power. So stuff like that. So change in the geometry, that is your operating response. Sorry, the change in geometry is scaling. Let me. So there are two things: scaling, that is geometry change, geometry scaled. Okay, and the other thing is operating response change, operating parameter changed. So in all these two equations, all these two cases, you can use this thing. So that is this, and then q by your n d cube for the model is your q by n d cube for the prototype. So these are the three scaling laws. Just like we had specific speed for the pump, here also in the turbine literature also a specific speed for the turbine is defined. That is a function of your cp and ch, and finally it comes out in this way. So as this is again another non-dimensional number as a function of two non-dimensional numbers, so this also the specific speed is constant when you are scaling or when operating performance is same. Only thing is it is expressed in terms of power, because power is what is important here, and there it was expressed in discharge. So there it was n root q by h 3 by 4, here it is n root p by h power 5 by 4. So that is how it is expressed. So this is all about scaling for the turbines. So now let's do one problem on the Pelton wheel. So let's do a problem on the Pelton wheel. A Pelton wheel has a mean bucket speed of 12 meters per second and is supplied with water at rate of 750 liters per second under head of 35 meters. The bucket deflects jet through an angle of 160 degrees, find the power developed and hydraulic efficiency. So these are the things. So we have already seen. Okay, so how is the jet getting deflected? The jet is getting deflected of 160. So this is total is 160. When total is 160, this is 20 and this is 10. This is 10. Sorry guys, sorry, this is 160 and this is also 160. So this is your 20 and this is your 20. So in our literature, phi is 20. The deviation angle is 320. This generally jet deflection angle means this is how it comes, this is how it goes. So this angle is your jet deflection angle, but in our analysis we measured phi, require phi. So that is 180 minus the jet deflection angle. So it is 20 degrees. So the power delivered, we have seen the power delivered is T omega, and we got an expression for that. If you refer back, it's rho q u r omega v minus u into 1 plus cos phi. So that is nothing but rho q u v minus u 1 plus cos phi. How do we get v? V is the velocity that comes on for the nozzle, and that is root 2 gh. So head is available. Okay, so rho is water, so density 10 power 3. Q is 750 liters per second. Liter is 10 power minus 3 meter cube per second. U is given as 12. V we can get from this, so V minus U, and U is already given as 12 meters per second. Head is 35. From that you can get V, and cos 20. So when everything is known, when you substitute, you get close to 238.8. Go to use a calculator, kilowatt. That is the power delivered. And efficiency, well, we derive an efficiency general formula, that is the power delivered by the kinetic energy. So this is the thing. So everything else is known here. U is known, V is known. So if you just substitute phi is 20, you get 96.6% efficiency. So this is all about efficiency for the hydraulic turbine. So its Pelton wheel is quite simple. Two things, power delivered and efficiency. These are the two things which you should know. And scaling is common for, so you have to just remember three equations each for turbine and pumps for scaling. So this is all about basics of turbo machinery for GATE.